Hello everyone. Today we are going to discuss about axle split parallel hybrid electric vehicles. In our previous video, I already explained about different configurations or different architectures available for the electrical vehicles. So like battery electrical vehicles and HEVs, that is hybrid electric vehicles, and PHEVs, plug-in electrical vehicles, and then we have also FCEVs. So in that I already discussed about BEVs and the different components and the working principle and level of electrification and all those things we have discussed in that video. And in the next one I discussed about also series hybrid electric vehicle and parallel hybrid electric vehicles also we have discussed in our previous video. And today we are going to focus or we are going to discuss about axle split parallel hybrid electric vehicle. So let us start now. So the concept of axle split parallel hybrid vehicle is looks like this. Actually, we have two energy sources, and the energy sources is going to drive the axles in two different axles. In a parallel hybrid vehicles, we parallel hybrid electric vehicles, we have two energy sources, but both of them are coupled in a same axle. And as per the requirement, we either drive the vehicle through IC engine or through the electric vehicle, electric battery or the motor, or together. We have IC engine as well as the motor driving the vehicle together. But here in this axle split parallel hybrid vehicles, we have this motor or the electrical energy source is connected in the rear side or rear wheels of the vehicle, and the IC engine is going to be connected in the front axle. So let us understand this, how it is connected, and what are the different things available in this in the upcoming slides. So here if you see, there is a small comparison between this split axle split parallel hybrid as well as the parallel hybrid vehicles. So the first picture here you can see this, this is a split axle parallel hybrid vehicle. So where you have the engine, transmission, and fuel tank, all these are coupled with the front axle, and then the rear wheel or the rear this one axle is connected with a battery, and then powertronic components, and then the motor controller and the motor. So here in this picture, the motors are coupled in the wheel itself. So we have two motors, so that there is no transmission available here, but it is directly connected to the wheels itself. If you see this parallel hybrid vehicle, so we have two different configuration, either is a double shaft or a single shaft. So the first picture, that is picture B, shows that we have a two shaft, that is one shaft connected to the electric motor, the another shaft is connected to the engine. So both coupled through the coupler, and it is connected to the front axle. If you see the second or the third picture of this page, you can see the engine and the motor is coupled in the same shaft, and this is coupled to the transmission, and it is connected to the front axle. So this is the different configurations and a simple comparison between the split axle and the parallel hybrid vehicles. So let us keep this in mind, that what do you mean by this double shaft mechanism, because we are going to discuss this in later slides. So what are the operating modes of this parallel split axle parallel hybrid vehicles? So first we can have the IC engine propelling the vehicle. So where the fuel will be taken to the engine will convert this fuel power into the mechanical power, and which will be given to the transmission, and it is connected to the front axle, and the vehicle moves forward or reverse. In the second scenario, where the motor propels the vehicle, so where the fuel and then this engine is going to be in an idle state, and the battery is going to deliver the power to the motor, and because of this power or the torque which is obtained from this motor, so the vehicle is going to move forward or reverse. The third one, so the IC engine plus motor propulsion, where we need a high torque, or where we need a the power requirement is high, where we can use like a the motor can be working as a boost for the IC engine. So the IC engine is going to deliver the maximum power, and also this motor is going to support to achieve or to reach the required power requirement for that particular condition. So where we have the energy delivered from the battery to the motor, as well as the engine is also delivering the power to this front axle. So both axles are driven with separately, and the torques are generated, but the speed of the system is going to be same. So this is the third mode, and the fourth mode where we are going to apply a brake when the vehicle goes in a slope. You are going to apply a brake. So during that time, when you press the brake pedal, when you are applying a brake, so this is going to be sensed by the brake pedal position sensor. So this is going to activate the regenerative process. By this time, the motor is going to act as a generator, and it is going to produce the electricity because of the pull what you have in the moment of inertia, the moment of what you have in the vehicle because of the speed, and that because of that the energy will be produced and it will go to the battery and it will store in the battery. So this is called a regenerative energy production. And the last mode where the engine is driving the vehicle, as well as the batteries are getting charged through the motor generator set in the rear axle. And so where we have this motor, so the motor is going to act as a generator now, which will produce the power and it will go and store in the battery. So these are the 5 different modes of operation for the split axle parallel hybrid vehicles. So the power flow in this mechanism, you are going to have a control unit. So we have to synchronize both of the energy sources. So we should have a control unit for making them to work together. Like we have a battery and inverter converter unit and motor generator setup. So these all for driving the rear axle, so which will be driven by the motor, and the motor can act as a generator as well when it is in a regenerative process or in the charging process. So during this time, the engine also delivers the power through the transmission and in the front axle. So this is the way it is the power flow takes place in this separated axle HEVs. How much power should be delivered from the engine and how much power will be delivered from the battery, or which one will work alone? Suppose in sometimes we have only IC engine alone driving the vehicle, and sometimes we have the motor alone driving the vehicle, or parallelly both work together. So in that case, when we have both sources acting together, which will deliver how much power, all those things will be controlled by this control unit. We will see that in the upcoming slides. We have the detailed information about it. So axle split hybrid powertrain. So we have a different name for this. This is a through the road, that is a TTR vehicles. It is very much similar to the parallel hybrid vehicle. The main difference is that we are going to have electrical propulsion system, including battery, electric motor, voltage bus, electrical accessories, and it is connected to rear axle, as I told you a little earlier. And the mechanical propulsion system, which is divided to fuel converter, clutch, and mechanical accessories linked to front axle. But if it is a parallel hybrid vehicle, so both are going to be connected in the same shaft, or which is going to be connected to the front axle itself. So this is a small difference. Because of linking electric motor to rear axle, transmitting of conventional vehicles to a TTR type vehicle is very simple. Because we are not going to change anything from the front axle, so the front axle will be driven by the IC engine. We are just going to add few things in the rear axle to aid or to convert this conventional vehicle into hybrid electric vehicles. The separate axle architecture offers some of the advantages of a conventional vehicle. It keeps the original engine and transmission unaltered because we are not going to change anything in the front. and adds an electrical traction system on the other axle. So we are going to add this electrical traction in the rear axle, so that it is going to give a advantage. It is also a four-wheel drive, which improves the traction on a slippery roads and reduces the tractive effort on a single tire. Conventional vehicles can be converted into HEVs easily in this method. However, the electric machines and the eventual differential gear system occupy a lot of space and may reduce available passenger space and luggage space. So, since we are introducing the rear axle with controlled by electric machine, so we need the electric motor, battery, and then the powertronic controllers and all those things. So, it is going to occupy place. So, because of that, we will lose a comfort for storing the storage space, and the drive number of passengers can sit. Those things will be affected. So this problem can be um, solved by having the electric motor is a single gear, and a single electric motor is replaced by two small sized electric motor that can be placed within the two in-wheel motors. So this is what we have seen in the previous picture. So we are going to connect two motors and the wheel itself, so that it is going to not have the transmission system. So because of that, you are going to save a lot of space, as well as it is going to be compact in size. Moreover, the batteries cannot be charged from the engine when the vehicle is at a standstill. So this point we will discuss little later. So let us see how the parallel hybrid, and then split axle vehicle torque relationship and speed relationship works. So first we will see the parallel hybrid vehicle. So this one, you can see here we have a engine and clutch and transmission, and we have a battery, motor controller, and motor, so which are connected to the same shaft. And so we have shaft number 1 and shaft number 2, and this is going to be connected to the torque coupling, and this is going to be connected to the front axle. So the speed versus torque characteristics of the engine is given here, and the speed versus torque characteristics of the motor is given here, and the equivalent, the total net torque versus speed characteristics is given here. So this is the torque versus speed characteristics of this parallel hybrid vehicle. So let us see how it looks for the TTR, or the axle split vehicle. So for the axle split vehicle, we are going to have the motor and motor controller in the rear side. So where we are going to have two motors coupled in the tire in the rear axle. So each motor torque versus speed characteristics looks like this, and in the front axle we are going to have the engine and the transmission, and the torque versus engine speed characteristics is shown like this. So the net torque and speed characteristics looks like this, and when you compare these characteristics, it looks almost same. Okay, so this is what we are going to try to conclude from these three slides. So the torque and the speed characteristics, though we have electric vehicle in the rear and engine in the front, and in the parallel hybrid it is connected in the same axle, but the characteristics curve, that is torque versus the speed characteristics curve, looks similar for both of them. Torque speed relationship and profile of TTR-IWM hybrid. The parallel hybrid vehicle is essentially a torque coupled system. So let us first understand what is how the parallel hybrid system coupled, so that we can understand how the split axle vehicles are coupled. Okay, so first let us understand parallel hybrid vehicle is essentially torque coupled system consisting of a mechanical coupled drivetrain. So this is important for a parallel hybrid vehicle. So it is coupled in a mechanical way, mechanically coupled drivetrain. A ordinary parallel hybrid has some form of coupling devices such as pulley, gear, or chain assembly, which adds together mechanical power from the two sources. So we know that we have a electrical source where we have the motor to give the power as well as the engine. So these two powers are being generated, and it is going to come in a different shaft or in the same shaft. And if it is coming in a different shaft, it is going to be connected to the same coupler through the pulley, or it is going to be connected with the gear or chain assemblies. So this is what they say. And figure below shows the parallel hybrid drivetrain represent a 3-port 2-degree of freedom mechanical system. So we are representing the parallel hybrid system with a this mechanical, this one 3-port system. So the first port represents the power, that is a torque and the speed from the IC engine. The second port shows the power or the torque and speed characteristics coming from the motor. And then the third one is the output, so where the in-wheel motor torque and speed will be shown here, which is represented. So here there's a power which is obtained in on the wheel, that is torque into speed, torque 3 and speed 3. The product of this is a summation of the power produced from the IC engine and the power produced from the a motor. So that is power produced from the IC engine, the torque 1 and speed 1. The product of this is a product, the power produced from the IC engine, and the product of this is a power produced from the motor. So the summation of these two will work on the wheel, provided the losses are considered negligible, or we are ignoring the losses. Torque output T3 can be expressed like this. So the total torque which you obtained on the wheels is a summation of torque obtained from the motor and torque obtained from the IC engine. So this is from the IC engine and this is from the motor. So the K1 and K2 are the gear ratio or kind of things. Okay, so the coupling method, what coupling method we have, based on that the K1 and K2 will be available. So again, it is also a summation of the torque produced from these two with gear ratio or whatever it is, the coupling method. So the contributing torque tau 1 and tau 2 are independent of each other and can be individually controlled. So the torque can be controlled individually, but the speed is not going to be controlled individually. So it is going to be same. So on wheel, what speed we obtain, omega 3, and the speed of the engine and the speed of the motor, all of them is going to be same. So but the omega 1 divided by the gear ratio and omega 2 divided by the gear ratio, because we are going to convert the motor speed with gear, and then finally it is going to go to the transmission, and similarly the engine speed and with the gear ratio, and finally it will be connected to the axle. So that's how it is, the speed is going to be same, but the torque is going to be controlled individually. So this is all about the parallel hybrid vehicles. But for the split axle vehicle, the TTR parallel hybrid is a torque coupled configuration. Again, this is a torque coupled configuration. But the IC engine and the electric motor are added up not through a coupling device. That means we are not going to have a gear or a pulley or chain mechanism to couple these two devices together. But how it is connected? It is connected through the vehicle chassis, wheel and road. That's why it is called as TTR. That is through the road vehicles. So wheel and road and chassis. That means it is not directly coupled. It is coupled through vehicle chassis, wheels and road. Okay, so it is topologically similar to dual shaft parallel configuration, since the motor and IC engine operates on the same separate drive axle. So little earlier I have shown one picture, so where all the components of the engine and engine related things are connected to one shaft, and all the components related to electric motor and battery, everything is connected to another shaft. So these two are connected in a common axle through a coupler. So this is what called a dual shaft mechanism. So that similar to that, so this split axle vehicle also is going to be like a dual shaft parallel hybrid configuration. So how the power is coupled there. Similarly, here also the power will be added up and it is coupled. But the coupling is through the vehicle chassis, wheels and roads. The torques can be individually controlled, but their speeds are governed by equation. In the case of retrofit conversion vehicles, the ICE is connected to a multi-gear transmission. Of course, this is going to be connected with a multi-gear configuration. But if the motors are connected in a wheel, so there is no transmission is going to be available. So that gear ratio is not going to be there. So if you see the total torque produced, so here total torque tau 3 is equals to K1 into tau 1 because of the gears are available for the engine, transmission is available. But for the tau 2, that is the motor is directly coupled, so there is no gear mechanisms, there is no transmission available, so there is no K2 parameter here. So it is considered as 1. And for the speed as well, so speed omega 3 equals to omega 1 by k1, so that is a gear ratio. But here for the omega 2 is, since it is directly coupled, so there is no gear ratio, so there is no k2 available here. So system architecture of a TTR IWM hybrid vehicles. So if you see the block diagram of this total system, it looks like this. So we have an energy management controller. So this is the art of the total system, which is going to control the total performance of this vehicle, where it is going to interconnect all the parameters. So where we are going to have a motor controller, battery. So this is one driving mechanism. The another mechanism we have fuel tank, and then engine, and the transmission, so which will be connected in the front axle. So this is another driving mechanism. Apart from that, we are going to get different inputs for the energy management controller. So like brake position, brake pedal, whether the brake is applied or not, and similarly accelerator pedal position, how much acceleration is given. So based on that, actually it is going to control the parameters for the engine as well as the parameters for the motor controllers. So the energy management controller is going to give the signal for the motor controller, and the motor controller is going to control the motor, and similarly the energy management controller is going to give the signal to the engine controller, so that the engine fuel input for the engine will be controlled, so that the power generated can be controlled and the speed can be altered. So for doing this work, the energy management system takes different inputs like a brake pedal position, whether it is a regenerative process, or it is in a charging process, or it is in a normal running process. And similarly accelerator pedal position, so based on that, the throttle positions can be controlled. The throttle position will enable the engine to give more or less fuel to the engine, so that the speed can be altered. Okay, and GUI, that is a graphical user interface, that is for helping the driver to understand what happens, and it shows all the parameters in the system. And the energy management system also takes the speed of engine and velocity, and also very importantly the battery state of charge. That means how much power is available in the battery, so that whether you can add up the motor for boosting the power for the vehicle, or whether you need to charge the battery. So these things, these informations can be obtained from the battery state of charge. So control block diagram of a retrofit TTR-IWM hybrid vehicle. So if you see this, it shows a detailed information about what happens. So accelerator pedal with position sensor. So how much acceleration is given, that input is given to energy management system here. Apart from that, we are getting also different inputs from different sensors. So vehicle speed, how much is the current speed, and we are getting the throttle position, actual throttle position, what is the actual throttle position as of now, and the engine RPM, how much is the speed of the engine, and For these are all for the engine side, and for the motor side we are also getting the battery SOC and motor RPM. So these are the inputs for the energy management system based on the current throttle position and based on the driver requirements demands. So either it will increase or decrease the throttle, so that the fuel input for the internal combustion engine can be increased or decreased. So the enhanced TPS, so that means this will give the signal to the engine control unit, so that the fuel input for the internal combustion engine, that is the injection and ignition parameters, can be changed, either it increase or decrease, the speed can be increased or decreased. So based on that, the power obtained from the internal combustion engine can be varied. So this is from the internal combustion engine. Similarly, here for the motor drive controller, also based on the battery bank availability and also the mode selection from the driver. So whether he needs a pure electric driving or combined mode, or whether you want to charge the battery. So these are all the inputs from the GUI to the HEV energy management system, also the motor RPM and things like that. So based on this informations, what happens, the HEV management system gives the control signals for this motor driver controller and MCU. So the MCU will give the control signals for the electric motor through the powertronic components like converters, energy converters. We have inverters and converter units. So the triggering pulses for the energy in an inverter and converter unit, so will be controlled, so that the electric motor speed can be controlled and the torque obtained also can be controlled. So the total torque what you are getting on the axle or the vehicle movement will be the summation of the torque obtained from the IC engine and the torque obtained from the electric motor. So the vehicle gets this information, and from this again it is giving the feedback to the system. So this is a closed loop system. So control system of a retrofit TTR-IWM hybrid, basic control with no control for this one. So let us see how the system works here. So the accelerator pedal will be pressed. So when you press this, it is coupled through the mechanical cable link, and which will be changing the mechanical throttle valve. So the mechanical throttle valve position will change. So that position is sensed by this throttle position sensor, and that gives us a input signal for the engine control unit. So based upon the throttle position, the engine will take the fuel from the fuel tank. So it will combust inside the internal combustion engine, and based on that it will produce the torque and power. So this total system works separately. There is no link for this, for the electrical part. So this total system works without any feedback or without any synchronization with the motor units. So the HEV energy management system, that is EMS. So where it is going to, the energy management system is going to control the motor control unit, and based upon the battery availability, things like that, it is going to whether it is going to charge or it is going to deliver the power to the motor, which is going to be decided from the energy management system. So this is a very basic configuration or a control system. Let us see what happens in the next method. So we are going to couple both system together, or we are going to connect both systems. So we are going to connect the engine system as well as the motor system through energy management system. So the energy management system is going to control both of them. So in the previous picture you can see only it is the energy management system is controlling only the motor or the electrical drive part, and the mechanical drive part is not controlled through energy management system. But in this picture you can see the energy management system is controlling both of them. So the accelerator pedal is being pressed, so the mechanical link is changing the mechanical throttle valve position. So based on the mechanical throttle valve position, so the input will be given to the the energy management system. So that is actual TPS, the actual TPS, the throttle position is given here. So how much it needs to be changed, that will be decided from the energy management system. So This is say for example, if the throttle is 50% opened, so this is my actual throttle position, but as per the load requirement I need to open, say for example, 60%. So this 10% we have to further open, so this will be decided by the energy management system here. So now the energy management system have a effective control over the energy engine as well as for the motor control. And also it can easily identify which drive is going to take more load. Say for example, the engine is going to take this much amount of power, and the sharing can be done. So the motor can give this much amount of power, and then the engine can give this much amount of power. Based on that, it is going to give the signal for the motor control unit. So how much power required from the motor, so based on that it is going to give the signal. So whether the motor should be coupled or not, so that will be on and off. So if it is coupled, how much power is required from the motor control unit, so that will be controlling the torque. So that's why I told you in the earlier one, so the torque can be controlled independently and the speed is going to be same. So it is going to be decided by this HEV, energy management system. So based on the requirement, how much the fuel should be taken, so the enhanced throttle position input will be given to the engine control unit. So based on that, the engine control unit will give the signal for throttle, again the opening the throttle, so that the fuel will be injected. So based on that, the IC engine will produce the enough amount of torque, and the vehicle will either speed up or it will reduce the speed. All right. The next one, the same thing, but here we have electronic throttle valve. So there is no mechanical coupling. You can see here there is a mechanical coupling here. So those things are removed in the advanced one. So where we have an accelerator pedal which is being pressed here. So instead of a throttle position input, we are going to take a actual accelerator pedal positions. So this is actually APS, not TPS. This is APS, accelerator pedal position. So each will be given to the HEV management system. So how much is pressed, how much the driver is pressing the accelerator pedal, so that position will be measured from the sensor, accelerator pedal position sensor. So this input will be given to the energy management system. So and how much power is coming from the motor, and how much power needs to be coming from the the control unit. So this difference, how much extra is needed, or how much is need to be reduced, so that will be decided by the energy management system here, which will give the signal to this control unit. So the control unit will decide whether to increase or decrease the throttle position, opening position. So based on that, the fuel can be injected more or fuel can be injected less, and based on that, the speed and torque can be changed. Okay, so this the throttle position sensor also gives the input for the engine. So either you take the input from the APS, or you take from the input from the TPS to control the speed and torque of the engine. So this is the advanced control system for split axle vehicles. So these are the different block diagrams, different configurations from the basic to advanced controls. So the vehicle axle split vehicle looks like this. So in the front axle we have this engine and engine based transmission, things like that, and in the rear axle we have the motor and motor based components like powertrain components, inverter, converter, all these things in the rear axle. So how it is being coupled, it is a link shown in this picture, and regenerative braking mode and motor generator sets and everything is shown in this picture. So example for this vehicle, we got 3008 hybrid powertrain. So here in the front axle is powered by 2-liter diesel engine, and coupled with a 6-gear automated manual transmission. The rear axle contains a 20 or 27 kilowatts permanent magnet electric machine coupled with single speed gearbox. So this is an example of split axle electric hybrid electric vehicles. So this is another picture of the same. Thank you.